Let me tell you a story, one you think you already know. You've seen the picture since grade school, a tiny little bead in the middle called the nucleus, and some smaller beads, electrons running around it like planets around the sun. Maybe the electrons are blue and the nucleus is red. Maybe they're green plastic balls hanging from wires. Doesn't matter. Every textbook, every children's museum, every logo for anything scientific has that picture somewhere, and it's wrong. It's not mostly wrong. It's not well. Technically, it's a simplification. No, it's completely wrong. The same way drawing a square to represent a giraffe is completely wrong. It's such an incorrect mental picture that the more you cling to it, the more confused you'll get about how atoms work, and the deeper a hole you'll dig yourself trying to explain things that don't make sense because the picture is nonsense. But don't feel bad. We've all been taught that picture. And we've all had it slowly pried out of our heads by the merciless logic of quantum mechanics. So I'm going to do something that will feel very uncomfortable. I'm going to take away that picture and replace it with something far stranger and far more beautiful and far less satisfying to the part of your mind that wants little tiny objects doing little tiny things. Because nature doesn't care that you want little balls. It just is what it is. Let's start small. Let's start with hydrogen. 1 proton, 1 electron. The kindergarten atom. You might imagine the proton sitting at the center, like a marble, and the electron maybe 100,000 times farther away, zipping around like a planet. I know exactly what picture is in your head. Now let me blow it up. Where the hell is the electron? You probably want to say something like the electron is on the left side right now, or the electron is orbiting counterclockwise, or the electron is in that region over there. But that's not what quantum mechanics says. And quantum mechanics, let me remind you, is not guesswork or philosophy or a bunch of pipe-smoking physicists arguing in a dusty room. Quantum mechanics is the most accurate, experimentally verified framework we have for describing nature. When we build transistors, lasers, nuclear magnetic resonance machines, every modern technology rests on the rock-solid correctness of quantum mechanics. And that theory says something very peculiar. The electron doesn't have definite position until you measure it. Not we don't know the position, not we haven't measured it. Not it's somewhere, but our probes are crude. No. The electron literally does not have a definite position. It has something else instead of wave function, a kind of probability amplitude spread over space that lets you calculate where you might find the electron if you choose to look. This is the first thing the old solar system model gets wrong. The electron is not a little speck going around the nucleus. It's a cloud of possibilities, a smeared out set of maybes. Not because the electron is actually smeared like butter. What's smeared is your knowledge, or rather, what nature permits you to know. When people say the electron is in a cloud, they usually imagine the electron is really somewhere in there, hiding like a pea under one of the shells in a street game, and we just don't know which shell it's under. That's not it. The pea isn't under any of the shells until you lift one. This is one of those ideas that makes your brain try to jump out of your skull because you've spent your entire life around objects that definitely are somewhere. Even if you don't know where your car keys are, they're in some definite place. They're not in a superposition on top of the fridge and also in your coat pocket, but the electron is. And the moment you measure it, its wave function, this spread out mathematical object, collapses into a single point. If that sounds weird, it's because it is weird. The universe is weird, and yet everything built out of atoms works flawlessly because of that weirdness. Why the orbit picture fails catastrophically? Let's pretend for a moment the old picture were right. Imagine the electron as a little charged marble whipping around the nucleus in a circle. Well, any charged particle that accelerates emits radiation light. And anything going in a circle is accelerating because its direction is constantly changing. And if the electron radiates light, it loses energy. If it loses energy, it spirals inward. You can calculate the time scale for that collapse. I assign this calculation as homework in some classes. It takes about 100 trillionth of a second. Poof. Gone. If electrons orbited like in that picture, atoms would collapse. Before you could finish the sentence, atoms would collapse. Chemistry wouldn't exist. Matter wouldn't exist. You certainly wouldn't exist, but atoms don't collapse. They're stable for billions of years. So that picture of circling electrons must be wrong. Then you might try the opposite picture. Okay, so the electron must just sit still. That doesn't work either, because quantum mechanics gives you the Heisenberg uncertainty principle. If the electron were sitting still with zero momentum, we know its position exactly and its momentum exactly. And nature slaps your wrist for trying to know both at once. You can't. The universe doesn't allow that state to exist, so the electron isn't orbiting. But it isn't sitting still. So what's it doing? It's not doing. It exists as a stationary wave function, a probability cloud. The cloud isn't a physical puff of mist. It's not made of anything. It's a mathematical object that tells you the odds. Only when you make a measurement do you get a particle. This is not an analogy. This is how real atoms behave in real experiments. Orbitals, not orbits, instead of paths. Electrons occupy orbitals. An orbital is a shape in space where the wave function has non-zero amplitude places where the electron might be found if you go looking. The simplest orbital, the hydrogen ground state, is a sphere, not a path, not a ring, a sphere of probability. Higher orbitals have weird shapes, dumbbells, donuts, four-leaf clovers. They look like something a sculptor would make after a few glasses of wine. But they are not actual shapes of actual objects. They are shapes of probability. Shapes of the wave function, the electron doesn't travel around these shapes. It is described by one of these shapes. And here comes another punch in the face. When an electron jumps from one orbital to another, it doesn't smoothly slide through intermediate shapes. It goes from one allowed state to another in a discontinuous step, a quantum jump, a leap with no classical analogy. Does it go through the space in between? No, not because it's too fast, because the wave function simply stops being one shape and becomes another shape. There is no intermediate state. If that sounds crazy, remember, we can measure the photons emitted by these jumps to 12, 14 decimal places. Quantum leaps happen, and they're as real gets. What is the electron really? You might ask, well, is the electron a wave or a particle? And the correct answer is, stop trying to force nature into categories that make you comfortable. Sometimes electrons behave like particles. You detect them as tiny localized events on a screen. Other times they behave like waves interfering, diffracting, doing all the things waves do. They're not either. They're quantum objects. They belong to a category that doesn't exist in your everyday life. A quantum object behaves like a wave until you measure it, and then it behaves like a particle. And no one fully understands what constitutes a measurement or what collapse really means. Entire careers are spent arguing about this. What we do know is the math works, the predictions match experiments, and everything you touch, see, breathe, and it comes from that math, add more electrons, and things get wild. Helium has 2 electrons. Carbon has 6. Iron has 26. In all these atoms, electrons are not little individuals with names and hats. Electrons are indistinguishable. Not very similar. Indistinguishable. If you swap 2 electrons, the universe would not change in any way you could measure except the wave function changes sign. Why? We don't know why. But if they didn't obey this rule, matter would not exist. That rule is called the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. This is why electrons pile up into different ENT orbitals. This is why chemistry exists. This is why you don't fall through the floor. Your feet don't hit anything. The electrons in your feet and the electrons in the floor are forbidden by pure mathematics from occupying the same quantum state. The universe says no. You stop there. And you stop. The solidity of matter is not solidness. It's arithmetic. Now, let's speak inside the nucleus. You might think the nucleus is the simple part. A bunch of protons and neutrons stuck together like grapes in a cluster. But protons and neutrons aren't fundamental. They're made of quarks, 3 quarks, each held together by gluons. But those quarks aren't sitting still. They're jittering, exchanging gluons, popping virtual quark-antiquark pairs in and out of existence. It's a party in there. And most of the mass of the proton, it's not from the quarks. The quarks are almost massless, most of. The proton's mass is the energy of the gluon field swirling inside it. E equal to mc2. Mass is energy. A proton is a little drop of trapped energy. And protons and neutrons are held together in the nucleus by the residual strong force mediated by pions, which themselves are made of quarks. You can think of it like Velcro if Velcro were made of vibrating energy field described by quantum chromodynamics. So what is actually inside an atom? Not particles, not little billiard balls, not tiny solar systems, not stuff. What's inside an atom is fields, quantum fields, the electron field, the quark field, D, the gluon field, the electromagnetic field. These fields fill all of space. They're everywhere. When we say an electron is in an atom, we mean the electron field has an excitation near that nucleus. Atoms are stable patterns in these fields. Matter is not stuff, it's structure, organization. Standing waves in fields, dancing mathematical patterns. You can ask, but what is the field made of? And the answer is, the field is not made of anything. It just is. It's a fundamental entity. Asking what it's made of is like asking what space is sitting on. The vacuum isn't empty. You may have heard the phrase atoms are mostly empty space. That's not quite true. The space around the nucleus isn't empty. Quantum fields live there. The electron's wave function fills that space. The vacuum seethes with virtual particles. And when you push your hand on a table, you're not feeling atoms colliding. You're feeling fields resisting fields. And the exclusion principle telling electrons to stay the hell away from each other. How big is an electron? As far as we know, zero. A point. No size. And yet the wave function describing where you might find the electron spreads over a region 10,000 times bigger than the nucleus. This is what I mean when I say, forget your classical pictures. They won't help you here. Spin, the thing that isn't spinning. Electrons have spin angular momentum, but they're point particles. So what's spinning? Nothing. Spin is intrinsic, a quantum number that behaves like angular momentum in the equations, but has no classical analog. Measure the spin along any axis and you get com1/2 and not anything else. Before you measure it, the spin is not really up or down. It's in a superposition. After you measure it, it snaps into one value, energy levels. Why the universe has colors. Electrons can only occupy certain allowed energies. Not because God likes whole numbers, but because the wave function must fit around the nucleus. Like a string fixed at both ends, only certain harmonics work. When electrons jump between these allowed states, they emit precise photons. And these photon wavelengths match our calculations down to absurd precision. Trying to look changes the thing you're looking at. To probe small scales, you need short wavelengths, which means high energy. And high energy disturbs the system. This isn't poor technology, it's fundamental. There is no such thing as a passive observation in quantum mechanics. The electron does not have a definite position until a measurement compels the universe to give you one. So what's an atom? An atom is a solution to the Schrödinger equation, a stable configuration of quantum fields, a pattern, not a thing, a rhythm, not a pebble, math masquerading as matter. Everything you see and touch, the solidity of the world, the diversity of chemistry, the shape of your body, the thoughts in your head, comes from these bizarre rules playing out at the smallest scales. If you feel unsatisfied, if you want something more real underneath it all, I understand. But nature is under no obligation to satisfy your preferences. The universe is not built for little billiard balls. It's built from mathematics that behaves in ways no classical picture can capture, and somehow, from all this strangeness, emerges the familiar world, the chairs, the trees, the cats, the humans, the galaxies. Patterns in fields, governed by equations, dancing their cosmic dance. If that leaves you a little dizzy, well, good. Physics is supposed to do that.